Hi guys. So we are now continuing Physics 113. We are going to spend the next couple of lectures learning about how to measure distances in astronomy and things about other galaxies, and we're going to move on to the topic of cosmology. So here's a galaxy, and there are some galaxies. There's a galaxy. That's the galaxy. There's a galaxy. Over there's probably a galaxy. There's a galaxy. There's lots of galaxies in this picture. They're all over. So, what do I want to say about galaxies? Well, a very natural question we could ask in astronomy is, where are all these things we see in the sky? We are standing on Earth. We look up at the night sky. We see a bunch of stars and planets and galaxies. In other words, can we make a map of the universe? So, measuring an object's location on the sky is easy. All you have to do is you have to open your eyes, look up, and see where it is. So in a way, you could kind of think of the location on the sky as just asking the question, what would the latitude, longitude of that object be on the sky? Now, this is often referred to as the celestial sphere, where we pretend that the Earth is at the center of a big sphere. All the objects are pinned down to the inside of that sphere, and then we go and we look, okay, where's that object on the sphere? Now, this is just a mental image. We are pretending every object is the same distance from the Earth. Obviously, this is not accurate, not the way nature really works, but this does kind of give an idea for where is the location of an object on the sky. Another way of thinking of this question is, if I were to pick any object on the sky at all, there is some location I could go to on the Earth where that object would be directly overhead. So where is this object on the sky is like asking, where on Earth would I have to go for this object to be directly overhead of me? Now, measuring the location on the sky, kind of like latitude, longitude on the sky, is easy. Measuring distance to objects is much more challenging. We can't send spacecraft to other stars. The Voyager spacecraft have been traveling for about 45 years and they barely left the solar system. If you think to the video, the dude had a pea representing the sun, and then the next star was a pea and a radish seed over 100 miles away. So we can't really travel to other objects that are outside the solar system to see where they are. Now, in the interest of trying to map the universe, in 1785, William Herschel, the same guy that discovered Uranus, he attempted to determine the size and shape of our galaxy. Now, when he was using his telescope in England to make a map of the universe, he made some assumptions. He assumed that all stars have the same intrinsic brightness, so every star is as bright as every other star. He also assumed that stars are more or less evenly spread out throughout the galaxy. And William Herschel also assumed that he was able to see the edge of the galaxy with his telescope. And in making his map of the universe, he came up with something that looks something like this, where he figured the sun was relatively close to the center of the galaxy. Now, as it turns out, all three of these assumptions were wrong. But keep in mind also, you can't hold it against him. He was asking this question and attempting to map the universe over 200 years ago in this late 1700s. So he was somewhat limited by the technology available to him at the time. Now, we did talk already about two different methods for measuring the distance to other objects in the universe. We talked about parallax and main sequence fitting. Parallax is the apparent motion of a nearby star compared to very far away stars at different times of the year. So when the Earth is over here in its orbit, this nearby star appears to be kind of by that twinkling magenta star over there. But 6 months later, the Earth is on the other side of the sun, elsewhere in its orbit. Now this nearby star appears to be kind of close to this dark blue star. So at different times of year, a nearby star will appear to change its relative position on the sky compared to some really, really far away objects. Now, technically, these objects are all at different distances, but kind of like in photography, if objects are at a whole bunch of different distances, but they're all really far away, you just pretend they're all infinitely far away and go from there. So, using trigonometry, it is possible to then calculate the distance from the sun to this nearby star if you can measure the shift in this angle. Now, the parallax method will work for relatively nearby stars. For about stars within about 3,000 light years of the sun, we can measure parallax. But beyond that distance, our technology cannot measure the parallax of other stars. Now, how far is 3,000 light years? Well, for comparison, our galaxy that we live in is over 100,000 light years across. So we could really only use parallax to measure the distance to some stars in our immediate neighborhood. Now, parallax was, even though the telescope was invented in 1608, and by 1610, Galileo was using a telescope for doing astronomy, parallax was not successfully measured until 1838, over 200 years after the telescope was invented. These angles, the angle that nearby stars appear to shift is incredibly, incredibly small. And even though the stars technically shift across the sky as the Earth appears to shift across the sky as the Earth moves around the sun, this angle is so small that we just didn't have the precision and the quality of optics in a telescope necessary to ever measure this parallax until the first half of the 19th century. So even the closest stars are really, really far away. As I mentioned in the previous module in 112, at the time, one argument in support of the sun going around the Earth was that ancient astronomers said, well, if the Earth traveled around the sun, you would expect some nearby stars to shift their position on the sky. And because we do not observe the shift of position of stars on the sky, the Earth cannot be going around the sun. Now, their reasoning is absolutely correct. The problem was the shift of the stars compared to very different distant stars is so slight that it was just too small to actually be observed. Now, another method for determining distances in astronomy that we talked about was main sequence fitting. Main sequence fitting employs the idea of standard candles. Now, I did not explicitly mention standard candles yet. The idea of a standard candle is, let's assume that there is some object in the sky, and to a reasonable degree of certainty, I understand what are the underlying physics going on in that type of object. So in other words, I know what that object is made of, I know how it works, I know how bright that object is supposed to be. And this assumes I know other underlying characteristics about the object. If I go out and I look at one of those objects, I could measure how bright that object appears. Now, if I know how bright that object appears, and if I know how bright that object really is, I could compare the apparent brightness to the absolute brightness and calculate the distance to the object. Obviously, if the object looks dimmer, it's going to be further away. And this is the idea of standard candles. The idea of using standard candles is going to come up again and again in many different techniques for measuring distances in astronomy and cosmology. We already talked about standard candles when we discussed main sequence fitting. Now, what we do is if we have a large group of stars that are relatively packed together closely, I could plot all of those stars on an HR diagram. So we talked about the HR diagram, how the brightness is related to the color of that star, color is related to temperature. And if I observe a whole bunch of those stars, the color I observe is not going to change, but the brightness of those stars will decrease the further and further away they are. So if I plot a whole make an HR diagram, and I see all the stars are lower than what they should be, I could turn that into the distance to that big cluster of stars, and then I know the distance to those stars. The dimmer those stars appear to me, then the further away those stars are. Now, notice how main sequence fitting uses the idea of standard candles. Again, I know how bright those stars should be because I have the HR diagram. I could record their color, know something about their temperature and their size. And if I know how bright they should be, and then I look at how bright they appear, I could turn that into a way to measure distance. So how could we measure the distance to faraway objects? And this is going to be the theme of today's lecture. So there are some methods of measuring distance. Some methods are better for closer objects. Some methods are better for more distant objects. So radar ranging is a method where we could measure the distance to objects in the solar system. All we have to do is we send a radio wave, bounce it off a planet, and then we wait for the return pulse, the echo, the reflection of that radio signal bounced off the planet. And if I record the time of travel, I know the speed of light, I could infer then how far away that planet is. There are parallax measurements that we described that are good for measuring the distance to nearby stars. Main sequence fitting we could use for pretty much stars in our galaxy. There are also Cepheid variable periods that will be very important for what I talk about today. There's the Tully-Fisher relation. Type 1a supernova is another very important type of distance measure, baryon acoustic oscillations, and Hubble's law. So radar ranging is useful for measuring the distance to objects in the solar system. Hubble's law is useful for measuring the distance to objects on the other side of the observable universe. So different techniques apply to different distances. So within the solar system, we have our radar ranging. Nearby stars, we could use parallax. In the Milky Way, we could use main sequence fitting. The Cepheid variable periods are useful for nearby galaxies. Hubble's law and type 1a supernova are useful for very distant objects. So what is a Cepheid variable star? All stars, the sun included, fluctuate to some degree in the amount of light they give out. And there are a whole bunch of different mechanisms that cause this. There are different reasons that stars will fluctuate in their brightness. Now, Cepheid variables are a very special type of star. For one thing, Cepheid variables are very bright. So if we're trying to see something really far away, we probably want it to be bright. It makes it easier to see. Cepheid variables also pulsate over a time scale of days or weeks. Now, the sun has a whole lot of different reasons that it fluctuates in the amount of light it gives off. It does not fluctuate much, but it is detectable. Now, imagine a star that changes its brightness over a period of 200 years. Well, this is not very useful because the time scale over which that star fluctuates in its light output, it's much longer than a human lifetime. So if I'm an astronomer, I would not be able to really do much useful science with that period of fluctuation. But an object that pulsates over a matter of days or weeks or months, this is something I could measure, and by tracking the brightness, the light output by that star, I could actually get some good data from that. Cepheid variables also pulsate in a predictable manner. They are not erratic in their light output, so they are predictable. And another very important property of a Cepheid is the rate of pulsation is directly related to the inherent brightness of that type of star. So let's focus on these two. Cepheid variables are very bright, and their rate of pulsation is directly related to their inherent luminosity, their inherent brightness. If we could find Cepheid variables in other galaxies, then that means it's possible to measure the distance to those faraway galaxies. And the Hubble Space Telescope's primary mission was to accurately measure the distance to Cepheid variable stars. This allows us to accurately measure the distance to these other galaxies. So I'm going to stop the lecture here, and I will continue with part 2 of this lecture in the next video.